Download this code from codegive.com, link in the description below. OK, let's delve into a comprehensive analysis of privacy risks associated with deep learning, covering concepts, techniques, code examples, and practical considerations. This will be a long and detailed guide, so grab a coffee, or your beverage of choice. Introduction: the privacy problem in deep learning. Deep learning models are incredibly powerful, but their training and use pose significant privacy challenges. These challenges stem from data dependence. Deep learning models are trained on vast amounts of sensitive data, example medical records, financial transactions, user behavior. This data often contains personally identifiable information, PII, or attributes that can be linked to individuals. Memorization. Deep neural networks can memorize aspects of their training data, making it possible to extract sensitive information through various attacks. Model sharing and accessibility. Pre-trained models are often shared openly for research and development. If these models were trained on private data, they can become vectors for privacy breaches. Regulatory landscape. Regulations like GDPR and CCPA mandate the protection of personal data, including data used in AI/ML systems. 2. Types of privacy attacks on deep learning. We'll explore several major categories of privacy attacks. 1. Membership inference attacks, missing in action. Goal to determine whether a specific data record was used in the training of a target model. How it works. An attacker trains a shadow model using data similar to the target model's training data. The shadow model's output on the target record is then used to infer its membership status. Intuition. Models often behave differently on data they've seen during training versus data they haven't. Code example, conceptual, using TensorFlow/Keras. Key points. The shadow model mimics the behavior of the target model. The more similar the shadow model and its training data are to the target model, the better the attack will perform. The attack model uses the output of the shadow model to distinguish between members, training data, and non-members. The accuracy of the attack model on the target model's predictions is the key metric for assessing vulnerability. This is a simplified example. Real-world MIAs are more sophisticated. 2. Attribute inference attacks, AIA. Goal to infer sensitive attributes about an individual based on the model's output. How it works. The attacker leverages knowledge about the model's training data and the correlation between different attributes to predict the value of a sensitive attribute that was not directly used for training. Example. Given a model trained to predict loan approval, an attacker might try to infer an individual's race or gender from their loan application and the model's output. Code example, conceptual. Key points. Correlation is crucial. If the sensitive attribute is independent of the other features, the attack will fail. The attacker model aims to predict the sensitive attribute based on the model's input features. The success of the attack depends on the strength of the correlation and the complexity of the model. 3. Model inversion attacks. Goal to reconstruct sensitive training data from the model's parameters or predictions. How it works. The attacker optimizes an input to maximize the model's output for a specific class. The optimized input is then interpreted as a reconstruction of the training data associated with that class. Example. Reconstructing faces from a facial recognition model. Conceptual code outline. 4. Differential privacy poisoning attacks. Goal inject data into the training set that allows for the recovery of private information. Asterisk how it works. Asterisk craft specific data points to be added to the training set which, while not severely impacting model utility, will, under differential privacy constraints, allow an attacker to make better inferences about private data. Because the injected data slightly skews the model, the privacy budget must be spent more aggressively to still provide epsilon, delta guarantees of DP, but the attacker still gets better than chance inference. Asterisk example asterisk training an image classification model with a small percentage of manipulated images of a specific person's face. Asterisk this is a more advanced attack. 3. Differential privacy, DP a defense mechanism. Differential privacy is a rigorous mathematical framework for quantifying and limiting the privacy risk associated with releasing information derived from a data set. One core idea asterisk add noise to the data or the model to obscure the contribution of any individual data record. 2. Formal definition asterisk an algorithm M is, epsilon, delta, differentially private if for any two adjacent data sets D and D, differing by at most one record, and for any set of possible outputs S, the following holds. Asterisk epsilon the privacy budget. A smaller epsilon provides stronger privacy guarantees but may negatively impact utility. Asterisk delta the probability of a privacy breach, even with epsilon differential privacy. It should be very small, example 10 sub-5/sub. 3 DP mechanisms asterisk Laplace mechanism asterisk adds Laplace noise to the output of a function. Suitable for numerical queries. Asterisk Gaussian mechanism asterisk adds Gaussian noise to the output. Asterisk exponential mechanism asterisk used for releasing non-numerical results, example selecting the best model. 4 differential privacy and deep learning asterisk differentially private stochastic gradient descent, DPSGD the most common approach for training differentially private deep learning models. Key steps 1 clipping clip the gradient of each data record to limit its influence. 2 noise addition add Gaussian noise to the clipped gradients. 3 averaging average the noisy gradients to update the model parameters. Privacy accounting track the accumulated privacy loss, epsilon, over multiple training iterations using techniques like the moments accountant or the Renyi differential privacy accountant. Privacy amplification using techniques like subsampling to amplify the privacy guarantees of DPSGD. 5 code example, DPSGD with TensorFlow privacy. Explanation L2 norm clip, limits the influence of each gradient. Noise multiplier, controls the amount of noise added. Higher values increase privacy but can hurt utility. Number microbatches, a technique to improve privacy and /or performance. Ideally set to equal the batch size. Compute DP SGD privacy, computes the privacy loss, epsilon, based on the training parameters. TensorFlow privacy library provides the tools for DPSGD. Important DPSGD often requires careful tuning of hyperparameters to achieve a good balance between privacy and utility. 4. Other privacy enhancing techniques. 1. Federated learning core idea train a model collaboratively across multiple devices, example smartphones, without directly sharing the data. How it works 1. Each device trains a local model on its own data. 2. The local model updates are sent to a central server. 3. The server aggregates the updates, example by averaging, to create a global model. 4. The global model is then redistributed to the devices. Asterisk privacy benefits. Asterisk data remains on the devices, reducing the risk of data breaches. Asterisk example libraries / frameworks. Asterisk TensorFlow Federated, PySYFT. 2 Homomorphic encryption, HE. Asterisk core idea. Asterisk perform computations on encrypted data without decrypting it. Asterisk how it works. Asterisk data is encrypted using a special encryption scheme that allows mathematical operations, example addition, multiplication, to be performed directly on the ciphertext. The result is also encrypted. Asterisk privacy benefits. Asterisk data is protected even during computation. Asterisk challenges. Asterisk computationally expensive, limited availability of ML frameworks with HE support. 3 Secure multi-party computation, SMPC. Asterisk core idea. Asterisk multiple parties can jointly compute a function on their private inputs without revealing their inputs to each other. Asterisk how it works. Asterisk data is split among the parties, and cryptographic protocols are used to perform the computation securely. Asterisk example. Asterisk training a model on data distributed across multiple hospitals without revealing patient records. 4 Data minimization and anonymization. Asterisk data minimization. Asterisk collect and use only the data that is strictly necessary for the intended purpose. Asterisk anonymization. Asterisk remove or redact identifying information from the data. Asterisk techniques. Asterisk suppression, removing specific data points, example names, addresses. Asterisk generalization, replacing specific values with broader categories, example replacing an exact age with an age range. Asterisk perturbation, adding noise to the data, example adding random noise to numerical values. Practical considerations. 1 Trade-offs. Asterisk privacy enhancements often come at a cost in terms of utility, example model accuracy, computational efficiency, and complexity. Carefully consider these trade-offs. 2 Context matters. Asterisk the best privacy strategy depends on the specific application, the sensitivity of the data, and the regulatory requirements. 3 Regular audits and monitoring. Asterisk continuously monitor the system for potential privacy vulnerabilities. 4 Transparency and user consent. Asterisk be transparent with users about how their data is being used and obtain their consent where necessary. 5 Stay up to date. Asterisk the field of privacy enhancing technologies is constantly evolving. Stay informed about the latest research and techniques. 6 Ethical considerations. Asterisk think beyond just complying with regulations. Consider the ethical implications of your AI/ML systems and prioritize responsible data handling. 7 Data governance. Asterisk establish clear data governance policies and procedures to ensure that data is handled securely and ethically throughout its life cycle. This includes data collection, storage, processing, and sharing. Implement data access controls to restrict access to sensitive data to authorized personnel only. 8 Risk assessment. Asterisk conduct a thorough risk assessment to identify potential privacy risks associated with your AI/ML systems. This includes identifying sensitive data, potential attack vectors, and the potential impact of a privacy breach. 6. Conclusion. Privacy in deep learning is a complex and multifaceted challenge. By understanding the different types of privacy attacks and implementing appropriate defense mechanisms, you can significantly reduce the risk of privacy breaches and build more trustworthy and ethical AI/ML systems. Remember that a layered approach, combining multiple privacy-enhancing techniques, is often the most effective strategy. Continuous monitoring, adaptation, and a commitment to ethical data practices are essential for navigating the evolving privacy landscape. The example code provides a foundation, but always consider the specific needs of your application and seek expert guidance when necessary. Good luck.